carrying on with transformations and stretching graphs and what have you. So dilations. Dilations is where we stretch the graphs to change the slope of the particular graph. If you want to change it horizontally, then horizontal is the domain, so it's the x values we're concerned with. So we replace x with x divided by a. So it becomes function x over a. Okay? So that will stretch it horizontally by a factor of a. Now if a is bigger than 1, so you're stretching it horizontally, that means the curve will become shallower. Think about think about a circle, maybe that's the easiest one. Think about a circle, you pull it out, then that slope of the circumference is going to get shallower. Okay? The domain might be altered depending on what the domain is. I mean, obviously if it was all real x, it's going to stay as all real x. But the domain might be affected, but the range won't change. The range should stay exactly the same. Now, if we want to stretch it the other way, vertically, so now we replace y with y divided by a. Okay, so y over a was equal to function x. Normally we see that with y being the subject, so we get y equals a times function x. Okay, so that'll stretch vertically. Now, think again of a circle. If you stretch that vertically, that's going to become steeper. And if a is greater than 1. This time, the domain should stay the same, but the range might change. On one graph, we're going to draw y equals x. There's y equals x. Y equals a half x. So what have we done to that? We can think of it as two ways. We can think of it as x divided by 2. So we're going to stretch it horizontally. Or if you thought about it as 2y is equal to x, then a would be a half. So now vertically would be, what would we do? Pushing it down, wouldn't we? So there's y equals a half x. So it became shallow. No, so we're pushing it down. I was right the first time. Yeah. I was confusing myself then. Now y equals 2x then would be the other way around. And so it would end up somewhere like that. It doesn't have to be straight lines, we can do it with any shape. So y equals x squared, there's y equals x squared. Now if we've got y equals a half x squared, this time I've got to be careful. Half x squared is definitely 2y equals x squared. I don't think of it as x squared on 2 because it needs to be grouped with the x if it was going to be a horizontal one. So I'll think of that one as 2y equals x squared. So that would be y divided by a half. So therefore we're pushing our parabola down. So we should get something that's underneath the original parabola. Okay. Whereas y equals 2x squared, think of that as y divided by 2 equals x squared. So now we'd be pulling the parabola up. There we go. Y equals 2x squared. So sketch x squared plus y squared on 4 is equal to 1. So it starts with the basic circle. X squared plus y squared is equal to 1. It's the y value we've affected. So y squared on 4 would be the same as y on 2 all squared. So we replace y with y on 2. So we're dividing by 2, that's a number bigger than 1, so we'd be stretching it out by a factor of 2. And we end up with an ellipse. Enlargements. To enlarge a shape, you apply the same dilation factor to both the x and the y value. So function xy would become function x over a, y over a. Replace with x over a, replace the y with y over a. So we've got a circle, x minus 1 squared plus y plus 2 squared is equal to 1. We're going to enlarge the circle by a factor of 2, using the origin as the centre of enlargement. So this is using the origin as the centre of enlargement. Find the new equation. Okay, so we replace both the x and the y. So it becomes x on 2 minus 1 squared plus y on 2 plus 2 squared. I suppose that is an equation, but let's get rid of those fractions. It would end up being x minus 2 squared plus y plus 4 squared, but that would equal 4. So your circle originally had a radius of 1, it's now got a radius of 2. which is what we would expect. We're enlarging it by a factor of 2. This bit I was talking about yesterday. Okay? Reflect before you translate. Okay? So not all transformations commute, can move around. Now, what is commuting with mathematical operations? A mathematical operation commutes if the order of the objects being operated on does not matter. Now, we've seen that in things like addition and multiplication. That does commute, because 3 times 4 same as 4 times 3. Whereas division and subtraction don't commute. 3 divided by 4 is not the same as 4 divided by 3. Okay, so some operations do, some operations don't. And that's the same with our transformations. So your transformations basically can be done in any order. The exception is this: a dilation and a translation in the same direction. So if they're both horizontal or they're both vertical. So here's a shape, and there I've done a reflection. So I've reflected it first horizontally. So reflect x equals 0, then I'll shift it right. So the reflection, a reflection by the way, is the same as a dilation of factor -1. So that's another way of thinking of a reflection. You could think of it as a dilation of a factor -1. So that's why we were saying yesterday, remember, reflection before translation. That's because the reflection is really a dilation, and dilation and translations don't commute. So the order is important. Now, number 2 over there would be if we shifted it first and then reflected. So we get different graphs depending on the order there. All right, so what will our equation become after we've shifted it up 1 unit and then reflected it? Shifted 1 up, x squared would become x squared plus 1. Reflect vertically is minus function x, so it'd be minus x squared plus 1, so we get y equals minus x squared minus 1. So that's when we shift it up 1, then reflect vertically. How about if we go the other way around? Reflect vertically, and then not the, reflect vertically, then shift it up 1 unit. So now x squared will become minus x squared, there's the reflection, and pull it up 1, you get minus x squared plus 1. So 2 different curves depending on the order that you did it in. You have a question. I have many questions.